pleasure to have our very own Nikolay Grantcharov speaking about the global Hecke object.
All right, well, thank you for the introduction, and thanks again to Justin, Kevin, and Nick this time for helping prepare this talk. Again, it would not have been possible without them. Okay, so what is the global Hecke action? So recall from Aaron's talk, we found that there was an action of reductive on sheaves on BunG, and this was done sort of pointwise. And what we're going to do is explain how to extend this action to sort of along the entire curve X. And the way we'll do this is by sort of like a chirohomology type of argument. And I'm going to, for simplicity, specialize to the Betti setting. And this is the so-called toy model of the four-author precursor paper by Kashdan, Rosenblum, and
Warshawski.
Warshawski. So things will be much simpler here. And in particular, the word restricted will not appear until the very end. So at the very end, I'll explain how to modify the definitions to generalize from this toy model to the full sheaf, like any sheaf theory setting. So this corresponds to setting A of GKRV. And this will be the main reference, and the other main reference will be this paper by Nadler and Yoon on the Betti spectral decomposition. So the setting, we have K, the ground field is the complex numbers, and X will be smooth projective curve over K, and G will be a reductive group. Okay. And let me just right away state the main goal for today. And we'll spend the entire day explaining how to prove this, is to construct a categorical action of quasi-co cis curve on sheaves of BunG, sheaves on BunG. And let me sort of, sheaves with nilpotent symbols. And let me sort of remind what both sides are saying. So on the first side, quasi-co fluxus G check of X. Sort of we define this, or Nick defined this to us using the Tanakian formalism. So on a test affine scheme S, it outputs right T exact monoidal functors from Rham check into local systems on X tensor quasi-co local system. Oh, space. Okay, this is an S, I apologize. And here, local systems means well, it's a subset of sheaves on this underlying topological space, consisting of complexes of sheaves whose cohomology sheaves are locally constant. So So again, I really want to emphasize that we allow all sheaves. We don't restrict to the inconstructible setting. So, there is a setting A prime of the toy model where we restrict to inconstructible sheaves. And then we have to put restricted local systems and replace local systems with quasi-lease. But we will not discuss that today. We just work with the most simple setting for the toy model. And yeah, so in particular, this correspondingly means just you take any representation of the fundamental group, not just the finite dimensional. And then on the other side, sheaves on BunG with nilpotent singular support. Again, it's all sheaves in this complex analytic topology. With singular support contained in this global nilpotent code. So again, recall this is just the zero section of the Hitchin map. And here, singular support is in the setting that Akil introduced to us, sort of the sense of Kashibara-Shapira. So vanishing cycles vanish. Okay. And here's sort of an outline of how we will construct this action. So first, I'm going to explain an equivalence of the left-hand side with some category involving rep G check. And this category I'll define shortly, but one way to phrase it, it's we take the chiral homology of rep check along X. So in particular, if X were any finite set, then it's just rep check tensor I many times. And using this equivalence, we can then reformulate the question of giving this action to giving a compatible system of actions on rep check on sheaf of BunG. And this is done by the geometric Satake. So this will be a pointer from rep G check tensor I tensor sheaves of BunG, and it goes to sheaves of BunG tensor quasi-co XI, or in other words, sheaves of BunG times X. And this is like what we'll discuss in the first half. Then we're going to use this result by Nadler and Yoon, and we'll sketch the proof of it, which says if you restrict to sheaves with nilpotent singular support, you will land in sheaves on BunG cross XEI with nilp times 0 singular support. So this means sort of this Hecke functor is locally constant along the curve X. Show each restricts to functor rep G check. Sheaf no BunG sheaf nil times 0 BunG times I. And then we will have our result, because you can decompose sort of sheaves on BunG cross XLI with this single support test. Like there's a tensor product decomposition that precisely gives you what you want. I'll explain this at the end. And then finally, like in the last 10 or so minutes, I'll explain how to modify these constructions for the Rham and etale set. So this is where we'll see the appearance of the word restrictive. To the Rham and the etale set. Okay. So let's begin. So first part is sort of just generalize about categorical actions. So I'm going to work with sort of symmetric monoidal DG categories. So A will denote some symmetric monoidal DG category. Sometimes I just refer to these as tensor categories for simplicity. And e.g., A will be reb-G check, or more generally, just quasi-co of some nice stack G, Z. And I will say what nice means. And then I will sort of move to this higher algebra setting. So instead of X being a smooth projective curve, I'll take its homotopy type. So it's not thought of as just in space. By taking homotopy type. And now comes the like key definition. I want to define what it means to take a tensor X in this general setting. So definition. So I'm taking a symmetric monoidal DG category, tensor space, and it's this co-limit of A. Now this is taking in sort of DG cat sim monoid. So I'm taking this co-limit along index category X of this constant functor X mapping to A. And it's taking in this symmetric monoidal. So that's the definition, but sort of to use it in practice, it's better to think of it in terms of universal property. So characterized by the following universal property. So maps from A tensor X into some other tensor category B. So A and B are tensor categories. And this now is taken in the category of tensor categories. This is defined to be just maps from A into B parameterized by X. So I'm using this superscript to denote it preserves this monoidal structure. And I want to sort of make a side remark here. If I remove the constraint of preserving monoidal structure, then I get something which maybe you are familiar with. So remark. We may define just a superscript x, and loosely speaking, this just maps from x into a by following universal property. And you can rewrite this space as maps from a tensor. Well, okay, let me do one more steps. So there's like two steps here. First, you use that taking local systems is dualizable. So I can replace x by local systems on x with the effect of replacing maps taking the category of spaces with taking maps in the category of DG category. And then I use, maybe I want to use A as dualizable. So then I can move the A on the other side. So it's just local systems x tensor x, A. And then the upshot is that this is AX is local systems on X tensor with A. So it's like maps from X into A. Now, when X is a finite set, both of these have very simple description. So if X equals I, finite set, then it's immediate that A tensor I is just A tensor A I times. And AI is A cross A. Right. Or in other words, maps from I into A. And also immediate from the universal property is that this definition commutes with taking co-limits in X. So if you can resolve X in a suitable sense by replacing X with some co-limit, then you can compute A tensor X by taking A tensor each of like the constituents, and then taking that co-limit. And we'll do that. Okay, and now the main theorem in this section of this red. So if X is a smooth projective curve, okay, and it's very important that we're working in the Betti setting for the proof I'll present. Then grab G check tensor X is Q of log sys. Right? And by the way, if you work, so the reason why GKRV call this A tensor X as the chiral homology of A along X is, so they also use the notation A tensor X to be this integral of A over X. The reason is that if you work inside in the Rham setting, you can show that the chiral homology satisfies the same universal property. That's why they call it. Okay, okay, so let's prove this main theorem in the first section. And to do this, it's actually easier to prove something slightly more general. We don't use anything specific about G.
Sorry, I have a question. This co-limit here, you say it's among just the constant functor from X to A that sends everything to just the,
From X to DGKRV, sim monoidal. So this is like the category of all symmetric monoidal tensor categories.
sure, but, how, in what way is X indexing things in? Constant diagram. Oh, this is a constant diagram, okay, sorry.
Yeah.
I thought that was.
That's right. But this is like how you should be thinking about it.
Property, sure.
I'm speaking on behalf of Nick here. Okay, so proof sketch. Or okay, so yeah, proof sketch. Easier to prove following. So suppose Z is a nice stack, which means one, that the diagonal embedding is affine. And two, that quasi-core of Z is dualizable. Okay, so of course, what we have in mind is Z is point mod G. So the quasi-core point mod G is rep G. And the diagonal in the setting is also affine. And then I'll formulate a more general thing where I replace rep G check by quasi-core of Z. So then I will call it theorem prime. Quasi-core of Z tensor X is equivalent to quasi-core of maps from X into Z. And again, when Z is point mod G, this is precisely local systems on X, which are G equivariant. Cover theorem by taking Z as point mod. And I'm going to, so I'll prove this, but let me simplify notation. I'll denote this space by Z superscript X. Here, yeah, just to sort of clarify, here Z is a stack and X is a space. Before I took a category. So, I mean, same idea, but yeah, there's a different meaning. Okay. Now let's construct a functor and show
X the underlying
space.
homotopy type. That's
Correct.
Okay.
Correct.
So in particular, maps X point mod G is not BunG in this case.
No. The slope is this exact same. This here.
Gotcha.
Okay, so yeah, let's prove this theorem. So to construct this map is pretty simple. I mean, there's only like two things you can use, and you use both. So first, rewrite X as maps from point into X, taking the category of spaces, and then just apply the functor maps into Z. So this is the reverse of theorem, it's contravariant. And now this is living in the category of stacks, free stacks. And then maps from X to Z, I denote by Z to the X. And maps from point to Z is of course Z. Okay, now I apply the functor quasi-core. And quasi-core stack is going to be some DG category. So when I write down tensor, I mean DG cat sim monoid. And this will be again a versus arrows. And this is precisely what we wanted. So again, this is characterized by universal property. So to define a map in this direction, it suffices to define a map from X into the mapping space of these. That's exactly what we did. We went from X to mapping space of QCO and QCO Z to X. So we have a map. QCO of Z tends to X to QCO of Z. Okay, now let me say if X were a point, we're of course done. No surprise. And slightly more generally, if X were a finite set, then because QCO is dualizable, you have this tensor product decomposition. So this becomes Z to the X becomes Z cross Z cross Z, and you can decompose. So we're done if X were a finite set. But X, of course, is not a finite set. So now what we need to do is sort of resolve X by a suitably nice space, and this is a very classical algebraic topology theorem. So you can rewrite X as a co-limit of wedge product of S1s. And yeah, Nick told me that this theorem actually predates Peter May.
Like age?
Yes. Yeah, with co-limits in DGCat and sorry, this is slightly. Yeah, just this code. And I'll write down a word with I being a so-called sifted
Is this actually very obvious if you think X is a CW complex or something like that?
yeah, that's as far as I could follow as well. So for S1, the diagram to keep in mind is point union point, maps the point, and then you take the homotopic push up.
Can you just say right away that in resolve X, you can always write X as a coordinate limit of just finite sets? What's the logic? Finite sets, right?
It's a sifted column of discrete sets.
Yeah. Finite sets.
Yeah, actually.
So how do you write it as a?
I mean, more or less by definition, because spaces are the same as quadratic preserving sheaves on finite sets.
They're saying the space has a triangulation, right? It's a geometric realization.
Yeah, that's okay.
That's close.
But it's more by definition.
Maybe I'm. Yeah, my weakness is in this infinite category space setting. I'll tell you. What I'll tell you.
You allow limits to be parameterized by that space.
Okay, so here's something which I know is true. I'm using X is a connected space over C. So I know that this is not true in the etale and the Rham setting. You cannot resolve X in such. What is it? Connected, just a topological space. Like
It only really makes sense in settings with but times, right?
Yeah, topological spaces.
it's a curve. It's a curve.
No, okay, so X is yeah,
Yeah.
right.
Yes. So
Like,
like
of course, we're getting a lot of that structure.
Taking the
but
homotopy type of
Yeah.
X of C.
Yeah.
Yeah.
But
Like this is like it is very worth stressing that you can only do this in the Betti set. Like the proof, there is an analogous theorem in the other two settings, but the proof is completely different. Here we use like what the original proof, like the toy model.
so data side makes some circles. Like S1s.
Yes. Sort of, yeah, we resolve X, and now the theorem sort of becomes formally follows from these two properties, but let me just write down the other two steps. For a wedge product of circles, you have that quasi-co commutes with push. So tensor wedge S1. And if you, I'll draw the diagram, but you can also rewrite this as quasi-co of Z tensor quasi-co of Z. And the tensor product is over quasi-co of Z to the I plus, where I'll explain this just shortly. You have the diagram I union base point, which I call I plus. You map the point in both ways. And if you take the homotopy push out, you get wedge S1 many times. So when I is just a single point here, point union point, and it's what I explained before. So this is just S1. And then yes, you take the same step. You first take maps into Z. So you sort of like raise Z to each of these powers, and then you take quasi-co of that. And you get this equivalence. Okay. So, and the reason why you can sort of commute co-limit push out with quasi-co is because of these two properties, dual isopole and affine. So that's it. And then step 3 is you do the same procedure on the right-hand side. So quasi-co of Zx is quasi-co of these wedges of S1s. And yes, with full limit in DGCAT, because I is SIP. So some nice property of this resolution is you have decided to SIP it, which allows you to compute the co-limit in DGCAT, as opposed to DGCAT with monoidal structure. And then, yeah, I ran out of space, but the final step is just to piece together step 1, 2, 3 to conclude. So, conclude. Quasi-co of Z tensor X by, definition of this tensor X, it commutes with co-limits, so I can write co-limit of Z tensor wedge S1. I'm using universal property plus step 1. And then I'm using now step 2 to write it in this way. And then step 3 is to, you get rid of the colon. So that concludes the proof.
And I think it just shows the defined sets. Right, wait. The same argument essentially. I think it's like from the point of view of high category theory, I think the statement of X can be written as equivalent to defined sets. It's even easier than.
So I'm a bit, I'm a bit suspicious because then you wouldn't need to use this assumption.
No, you use this assumption because I think the point is that if the diagonal is not defined, then it's not true that like this is not necessarily going to be a full Betti. Because you're using oh wait, I see.
I think it might actually be to shoot the right hand side. It's probably if Q of C is C is nice, then this Q of C and the X is the same thing as like X. That's like the
No, I think the sort of conditions on Z are important. The importance of some equation is coordinates.
it's sort of the right side.
Although I mean, why is it called coordinates? Since coordinates students. Right. Oh, but you have to. I don't know, but this is going to be L limit, not the full limit. Yeah. No, so actually interpretation is limits. I think for that we need to be right there.
I will get back to you. That's a fantastic question. I too thought like you can just look at finite set, but I'm a bit uneasy. Because like you really need to use like this.
Yeah, but where do you use it? It's a very argument.
But loosely speaking, you have to like understand, like you have to use like the fact that this is in some sense chiral homology. So like we need to like have some say like what happens when the points collide.
No, sorry, but where do you use the argument that diagonal? Where do you use the fact that diagonal is high?
In step 2 and 3.
Step 2, yeah. So,
Yeah,
because
so-
otherwise it's not going to be full back.
Yeah,
It may not be full back.
yeah. Like if this were just like vect, then I don't need affine diagonal.
Isn't the issue that is it true that no, mind. Yeah, I understand you didn't exactly argument, but do you know for sure that it's not true? It might not be true when the diagonal is not defined.
No, I can't say for certainty, but I strongly suspect I really do.
Maybe it's true
But I'm sure.
for any respect.
Can you say it one more time? Sorry. What was the proof of step 3? How do you pull this code out?
Yeah, I don't know. I know that you have to use both axioms that the diagonals affine and quasi-coordinates.
Basically one.
But I know it's a true state.
At some point, it's like you're pulling a.
I do need that it's sifted. Like I can
Right, but that's just so that you can say the pull up the state of DG categories, like you said.
yeah, but that's important.
Sure. But like, let's say you have a sifted code, right? Then your certainly maps out of the limit is going to be the limit of the maps.
Yeah.
So at some point you get Q of a limit, and then you're pulling that out and saying Q of a limit is the pull limit.
Yes.
Yeah.
Right, so there's something happening.
So this is
That's
something
has to do with the dualizability of Q of C.
So maybe I find that.
Let me get back to on that as well.
Sorry,
great question.
Yeah, this is the main.
I think there's a reason why connected spaces works. Plug in connected spaces works.
So what I like is that he told me like in the general version of the 6th author paper, instead of resolving X, he resolved the category C. I don't know what he meant. Like they don't touch X.
C,
Yeah.
under category.
I mean, you have two options. Like you want to show something about Z and X, So instead of like doing something with X, you do something with C. But he didn't elaborate on that, but like there is a completely independent proof. But here I think this is the most straightforward.
I mean, there's not much meaning to quasi-coherent in the X direction, because X is just a space. It's only quasi-coherent in the C direction.
Okay, so let me continue with our story. So now the upshot of this theorem is to give an action of quasi-co on anything, you can give an action of that space. And what that means, written out, is so. Quasi-co locus of X on M, and M, I will just think of, I mean, it's just a tensor category. And also, I want it to be dualized. So this is equivalent to giving, by our theorem, family of actions of Rham G check tensor I. Together with compatibility. That when you have a finite set J mapping into I, make sure I have I and J in the correct order. I maps to J. Then there's a commutative diagram. So yeah, when I say something acts on M, I mean exactly there's a monoidal functor from Rham G to endomorphisms M tensor sheaves on X.
So the first part is that given action of classical LS check X, yeah, it's the same as giving this compatible system.
Yes, for all finite sets.
And then you conclude that when you have that, I have this commutative diagram. Right? With commutative diagram part of this data.
Part of the data.
Okay, it's part of the data.
Yeah.
Basically,
and this is like analogous to like the Carl algebra, just compatible.
Why, where is this diagram coming from?
So giving an action of Rham G on M is the same as giving a monoidal functor from Rham G to endomorphism of M tensor sheaves on X.
Where is X in there? See the X, I see X below, but I don't see it.
Sorry, no, that's great.
Sorry, I don't think there's a Rham G check tensor I actually on M. I think it's just have this functor for Rham G check tensor I to n to the M tensor LS of X to the I. You have all these.
Just
Yeah, that
For every finite set, you have a horizontal functor. Square.
yes. There was an X here which somehow I erased here. Sorry. Great catch. Thank you so much. I apologize. Okay, so let me go from the beginning. Giving an action of quasi-co locus X G check on M is the same as giving a compatible family of actions for each finite set from rev-g check tensor I to end M tensor local exists index TDI, and then this commutative diagram plus some higher algebra. Okay, so
It doesn't need to be a tensor.
okay, sure. M of course for us will be sheaves on BunG.
You're not using.
Yeah, I'm not using anything about M. Fine, but I do want to use that it's dualizable so that I can split this endomorphism of M. So that's like I rewrite as tensor M here, and then like I write M endomorphism of M as M tensor M dual, and then I move the dual on the other side. Yeah, and then in the final 10 minutes before the break, I'll explain where this functor comes from for our setting of the Hecke action. Whatever you
It's really a lens.
I think it's gonna be at 30 minutes.
So step two. So I have to remind you a few definitions of what the Hecke stack is. So recall, well, this is like the I-legged Hecke stack. And I'll define it as like using the Tanakian formalism. Sorry, no, I'll define it in the usual sense. So on a test affine scheme S, it outputs all inflection data. So there's an I-tuple of points on X, a pair of bundles, G bundles on X, and an identification of these bundles generically. So this is S points of X I many times, P prime and P double prime on GX. S points, and alpha is an isomorphism away from this the graph. So this is the global Hecke stack. Now you can also define a local Hecke stack, where it's the same data, but just restricted to the disk. So same data. X I still an I-tuple of points in the curve. But now your bundles are defined on the disk. So I'll use this notation and explain it. So this disk subscript xi denotes you have the graph of this I-tuple of points into S cross X, and then you take formal completion of that. So when S is like a point, you just get like I many balls around the points. And then now your alpha is just an identification along the open disk. Okay, I'm gonna run out of space here. So D-cert means open disk. Okay. And then yes, there's going to be a restriction map, which I'll denote by R. Okay, and now let's recall the main theorem of geometric succession.
Can I ask a
Yeah.
real stupid question? Why do you need to use all collections of finite points over on this side? If we have it for just I equals 1, is it obvious that it doesn't suffice, that you can't, there's not like a unique extension to all the higher powers? Questions to our team, and we
And I also a little confused because why would have anything to do with the line sets? It's quasi-cobalt unless it's just a symmetrical case within.
Yeah, so for
What's
instance,
so special about it? What's so special about LS sheet check? So that you need this data for all finite sites.
Well, for your question, it's just the identification that quasi-co LSX is the same as Rev G tensor X. And then this tensor X,
But shouldn't you have only those I which appear in the presentation? X?
sure, yeah.
No, but is it for all finite sets or like or for the diagram, particular diagram? Which works, which presents X?
By definition, it's for all finite sets. But then if you use this theorem, step 1, then you can just specialize to like,
No, it's a special case, it's not.
yeah,
It's one exception.
Yeah.
It's not equivalent, I think it's more.
Yeah.
I mean, I don't know.
no, and for your question, I think it's the same answer. Like this is it's equivalent to Rev G tensor X. It's not just Rev G. Like you have to specify an actual Rev G tensor X. And this is a lot of data. Like you can't just say it suffices to check for X as a point.
yeah, because the X does appear then if I was 1 on the right-hand side, which is why I was slightly confused, but then.
So one thing maybe that's going on here is that like end of M is not a symmetrical category. So what you gave was a presentation of Cubo of Luxus as a colimit in symmetric G categories. Yeah, right. That's what this tensor power X is. So in particular, you know how to give a symmetric modal functor for that category. It's a symmetric modal category, but end of M is not symmetrical. Just you know what I mean? So it's like
So that's why you have to include all the higher data.
well, that's one reason why it's you think this would be able to say that just
I see.
maybe.
No, sorry, I just said it's actually it's sort of been a running
No, but
question in my head, but it's never been written out this explicitly.
But no,
It's
in my head, like you have to specify an action of Rev G tensor X. And your question is, can you just replace X by a point? And the question is, the answer is
No. It's saying replace I by
no,
right?
that's the same thing.
no,
No.
it's LSX.
Functor from F check the end of M tensor LS of X, right?
It's even more complicated than, like, we just want to construct a map, a monoidal functor from quasi-co LS G-check X to an homomorphic map, right? And actually, but this thing, the thing that X is a code, it's a coordinate of this rep G check tensor I guys for all i's mapping to X. For all finite sets mapping to X. Yes.
For all I mapping to X.
Yeah, I mean, sort of by that argument, basically.
You're definitely right. It completely does follow. Like.
Yeah, but I'm saying
And
that
we're
it's
replacing X with the
less data.
That's fine, yes.
Just you want to construct a functor from rep G check tensor I to endomorphism of M. So the for all I appearing the presentation of X. No, that sounds
This sounds plausible to me. Yeah. I mean, you're just using the presentation.
Nice. Oh, I see.
Like, I think Kirill is just saying you can use only these I sub i's which appear in this.
But then I don't understand why this tensor functor. I understand the utility.
Yeah, no, it was the size of.
Maybe
a slightly tricky point regarding the,
Yeah,
Regarding
okay,
the-
but let me just draw this Hecke correspondence. or sorry, let me state geometry Satake and then use that too. So. So I'll state it in the version where you allow I to be any finite set, not just a point. So there exists a monoidal functor phi sub I from the underlying abelian category of Rham tensor I onto this sheaves on this Hecke stack, local Hecke stack. And yeah, so again, the underlying the hard structure. And this is an equivalent when I is a point. And in general, it's just saying that there exists. In general, it just says that there exists a functor from here to here. And furthermore, this functor is T exact. So we may extend it to the full category. So we have this functor which I'll denote by S for Satake, from Rham G check, tensor I, to sheaves on this Hecke local stack. And I'll say a representation V maps to S subscript V. Now the correspondence diagrams for the Hecke modification following. So upstairs we have Hecke sub I, and it emits two projections to BunG, one on the left and one on the right. And then I can also map to the local Hecke stack by restricting to the diagonal. So R denotes restriction. And then from the local Hecke stack, I can further project just to the curve. And now we can conclude. So we call this the Hecke functor. It's a map which is defined for any representation. So let V be a representation of Rham G check. And then I define this functor from sheaves on BunG to sheaves on BunG times XLI. And what it does is it takes F and then you twist F by Satake. So now you have a sheaf over here. You pull back. And then you push forward. And by the way, these maps have nice properties. They are smooth. So this one on the left is smooth, and on the right it's proper.
So what would you mean by this? Sorry, I was. Right.
So again, I have a sheaf on BunG. I twist it by the Hecke, by the Satake. Then I pull back to this global Hecke stack and push forward back down to BunG. And this is exactly what we wanted. So I can rewrite this sheaves BunG times XEI as sheaves XEI, and sort of this accomplishes what we want. Now, after the break, I'll show that if you restrict to nilpotent here, you land in nilpotent. Take a break. All right, so now just recall we constructed this Hecke functor from sheaves on BunG to sheaves on BunG tensor sheaves on XLI. And what I'm going to do is show that if you restrict to sheaves with nilpotent singular support, you will land in sheaves with nilpotent singular support. And this is a theorem due to Nadler and Yu. So this will be like the most explicit part of the talk today. So there will be no usage of like any fancy words. The Hecke functor restricts to a functor so I'll replace the word nil with curly n. All right, so let's give a sketch of this proof. So there's several steps. Okay, first, yeah, so H is a map from G check tensor I, insert sheaves G. So first I can just assume I is a point by associativity of this action. So let me assume right, if I can show the seminar for I equals a point, then I use the tensor product decomposition of sheaves. So yeah, like I do rev G tensor sheaves BunG, then I do another rev G tensor that, and so on. So just by associativity. And now recall two very important properties about singular support. So if you forget what singular support means, that's okay. You just need to remember it has these two properties with respect to smooth pull back and proper push forward. Excuse me, smooth push forward and proper pull back. So recall two characteristics of singular support, which I'll denote by SS, with respect to smooth push forward. So this is the left arrow and proper. So I think I do. Yeah, this is a typo in my notes, and as I was writing it, I realized, yeah, of course I want to do this one. So yeah, I need smooth pullback. Yeah, you're right. Thank you. Yes, so I want to pull back the smooth thing and push forward. Yeah, okay. So this is the property. So I mean, let me sort of write it in the following way. Suppose F is a map of smooth schemes, then you have the diagram I mean, I can assume there's stacks, but let me just say scheme. You have a diagram. So this one is taking the differential, and this one is sort of like projecting to here, which I mean, I don't know what the standard notation is, but now we're going to call it F sharp. And let me also introduce notation, sort of the map in this direction. So if I take inverse image and then image, I'll call this df lower star. And then the map here, I'll call it df upper star. So let me write this down. So it could be F, and then F. Okay.
But these are factors between sheaves. Probably.
Yeah, it's a bit abusive notation, but oh no,
You want upper shriek pull back, that followed by lower.
yeah, I don't know what to denote these by. This is just notation. I'm defined. This is just notation. So the main property of singular support is the following. Okay. And okay, it's way up there. Let me just recycle the diagram. So yeah, this is the property. Okay, so we assume F has nilpotent singular support. And what we're going to do is show that the right-hand side has singular support inside nil times 0. So when I pull back, push forward, I land in the cotangent bundle of BunG times XI. So this is inside. Okay, and I'm going to show it actually lands in n cross 0. So let me spell out in symbols the statement we wish to show. So consider a pair of covectors inside the singular support of this sheaf on BunG twisted by Satake. And then this singular support, I mean, it respects external product. So in particular, C prime lives inside the global nilpotent column. And then consider another pair inside the singular support of the image of Hecke, such that it lives in the right-hand side. And what it means to live in the right-hand side is that the pullback of the two differentials agree. Okay. So we want to show one, that C prime prime lives in N. And two, that Cx is in fact 0. So I want to show this like constant along the X direction. Great. Now everything is sort of this fun computation. So what we do is we take the fiber of this diagram over some point of X. So consider I will have space. But let me actually use a new board. Sorry. Consider fiber over X. And then I consider the cotangent space of this f of X. And then I have P star 1G cross 2 star of this law. And then 2 star 1G. And then the arrows reverse. So it's and the X factor disappears because I'm taking fiber. So this. Great. Now I can also just specialize to a point of this Hecke stack. So I'll write it small. So pair of bundles P prime, P double prime, and the gluing alpha. And then here I have P prime, here I have P prime prime, and then here I have like the same data. But restricted to the disk. Okay. Now we've actually computed all of these cotangent spaces very explicitly in previous quarters. In fact, I did this. So we call T star P prime 1G is H1 of X associated G sub P prime. Cool. So this is global sections G sub P star tensor 1 forms. And we can not much with much more work actually compute the cotangent space of both Hecke stacks. So Hecke X. So what is this? Well, it'll again be the dual of some K, where K is the cone of this inclusion. That's correct. Is the cone of this inclusion into space. Prime. This is isomorphic to G sub P prime prime. So J is this open embedding of X minus points into X. And then I restrict G sub P prime to this open curve, and then I push forward. And these are isomorphic because of alpha. Okay, and then I can do the same for the local Hecke stack, where instead of X, I replace it with the disk. And we can write this as a vector space quite explicitly as a pair of covectors inside GKRV star. So this is what it means to live sort of inside here, but to be in a cone means there's some additional compatibility. The compatibility is that they agree when you restrict to the disk. I want X because I want this. Sorry, thank you. Yeah, thanks. Then I restrict to the open disk. Yeah. Yeah. Okay, and with this identification, then I claim we have done half of the work. So then the differentials, like the DH left arrow and the DH right arrow, just correspond to the inclusions. And here I mean sum, like in the sense of vector spaces, not direct sum. So this is a DH left arrow pullback. And this DH right. Okay, and then we're gonna write it. So let me call this equation dagger. So if I take the fiber of dagger over little x, again, the S factor disappears. S is the map into x. So it's differential of 0. So it's DH pullback of C prime plus DR pullback of C H equals DH right arrow pullback C prime prime. And now CH already lives in the Hecke stack. So this means that the difference between these two lives in the Hecke stack, the cotangent space. But to be in the cotangent space precisely means that there's this compatibility. And then it says, okay, in alpha isomorphism. So it says this guy is nilpotent if and only if this guy is nilpotent. And then having a covector whose restriction to the open disk being nilpotent is equivalent to the vector itself being nilpotent. So then we're done. So thus C prime is nilpotent. We can only have its restriction to the open disk is nilpotent. And then I'm using this equation. We can only have C prime prime restricted to the open disk nilpotent if and only if C prime prime nilpotent. So we're done with half. Now let's explain why this factor psi x is in fact 0. This one, I mean, sort of just give a quick summary of what like the computation boils down to. So it remains to show psi x equals 0. So there's a short exact sequence. So we have the cotangent space of the curve to the cotangent space of the Hecke stack. And this maps to the cotangent of Hecke at little x. And there exists a canonical splitting. This is just a fact. And what this tells us is that to check something is 0 here, it suffices. Sorry, to check something is 0 here, it suffices to check the image under this is 0. So I'll write this explicitly. Suffices to check if psi h in the cotangent space of Hecke x is in the senior support of Satake V. Then image of psi h under splitting is 0. Okay. So the image of this is psi x. Okay. Now here's what the argument boils down to. This question is local, so we can replace the curve by a1 and just assume x is the origin. And then we can actually compute this splitting explicitly. There's like a very explicit formula. And let me write down what this formula looks like. So we may assume and then a point of the Hecke stack corresponds under uniformization to the data. So remember, uniformization means you can write the local Hecke stack as this double quotient. So you can pick out a transition matrix. So big K here denotes field of Laurent polynomials, and O is like the regular part plus some compatibility, like so you have some G, and then by Cartan decomposition, you can express this double quotient as like a union over parameterized by regular dominant weights. So you can just assume that this representative is a nice form, namely it's diagonal. So here I'm identifying a coordinate T. Make this identification. Okay, and now let me write down what the splitting looks like. So it's a map from the cotangent space of the local Hecke stack at the point here. And it's a map into the cotangent space of X, namely just C. And what it does, so, okay, first, the tangent space of the Hecke stack is factor GK mod GO plus GO, but it's not really GO plus GO, it's GO plus add sub G of GO, or I mean this G. And if you dualize this, so the quotient of a sum of a sum of vector spaces becomes the intersection of their duals. So I can just write this as the intersection of the dual. Okay, and now what it does is it maps a covector C. So it's like a one. It's like here. And it's the residue. So you pair C with the logarithmic derivative of G. So it's lambda T inverse. And this is just the formula. You know, our question boils down to is, suppose this is nilpotent, show the image is zero. This is like easy exercise. Like it follows basically by looking at like the triangular decomposition of the object. I'll put a black box there. Okay, so that completes the proof of this Nadler-Yoon result. And there's one final step to sort of finish the construction of the global Hecke action in the Betti setting, and then I'll pause for questions and move to the general framework. So final ingredient is that sheaves on just any space is X and Y with singular support along two Lagrangians is the same thing as sheaves on X tensor sheaves on Y with the respective singular support. And this is completely general. So for us, of course, n prime will be the zero section. And n is n. And x is BunG, y is x to the I. And yeah, this sort of tensor product decomposition only holds in the Betti setting. Okay. So yeah, are there any questions? So summary, we constructed the Hecke action. We showed that its restriction to the nilpotent cone single support gives you nilpotent single support. And then, so yeah, then we have finished the construction. Yeah.
So like over time, this if only is at the bottom of the board here, how does that equation?
This one?
Yeah. So what happened to the sub H?
Yeah. So this is how I understood it. Maybe it's slightly faulty, but this is how I understood it. So you have psi H lives in the Hecke stack. The tangent space, the potential space.
Yeah.
Yeah. Okay. So now it's saying that this is equal to this minus this.
Right.
But under this identification, this must map to this one, and this must map to that one. So I think with this identification, the DHX for star C prime is precisely this expression, and this one is precisely that expression. And it's saying the compatibility is saying that
So is the point that the second term of the left-hand equation involves C sub H that might restrict to the pressure disk it vanishes? Yeah,
so no, not that it vanishes, that I mean the claim is just that the pair this minus that is precisely a pair like this. That is sort of I want to say that this equation implies that this tuple corresponds exactly to such a. Well, I'm unable to say it.
No, I believe it. It's me.
I mean, I'm unable to say it in a better way than that. Sort of. Since this is in the Hecke stack, it automatically satisfies the property, so it means that it's also.
Got it. Okay. That makes sense.
Yeah, it's not saying that this vanishes, it's saying that this pair is. Yeah, any other question? Okay. General stuff. Okay, so let's upgrade to the Rham and Betti. So now I'll just give you the constructions. I will not give any proof. So first, replace Loxis G check with a restricted local system. And I'll remind the definition of restricted local system. It's again using Tanaki. It looks very similar to the first formula I mentioned at the very beginning, with the exception that I replaced LS of X with quasi-lease. And quasi-lease, the definition depends on which sheaf theory you're working with. Maybe to save some time, I will just say verbally. So in the Betti setting, it's actually different from what I said. So in the Betti setting, you say quasi-lease of X consists of all complexes of sheaves which are inconstructible and whose cohomology groups are locally constant. So it's like you're working this inconstructible setting, which is smaller than all sheaves. In the etale setting, you do the similar thing, like you work with L-lattice sheaves, which are inconstructible and in local cohomology, locally constant cohomology. And then in the D-module setting, the Rham setting, again, you just work with int regular local systems. So those are the three symbols. And then the analogs of the main theorem in part 2 of my talk is the following. So this is theorem 8.3.7 of the 6th author paper.
No way. Oh, 6 off the paper, sorry.
And it says that rep
Or paper.
G check tensor X lease. I will explain what this is in a second. Okay. G check. Is equivalent to quasi-co local systems restricted. So what is cohom? I can give you a definition using universal property. If you ask me again, but let me say the following. If you replace quasi-lease with loxis, you precisely pick up tensor x as before. So rep G check. So it's some sort of refinement. Do you want me to explain? Yes, yes. Yeah, so remember, yeah, when I defined this using universal property, I said it's a map from rep G check to B, which is parameterized by X. But now instead of saying I look at maps from rep G check into B, I look at maps, or I just look at the tensor product. So instead of the map being space from here to here, I look at the tensor product from here to here, parameterized by X points. Sort of, yeah, it's the great. Now, another like a point I want to emphasize is that this is quite different from what we proved. Even in the Betti setting, this is there's more work needed to be done. So we proved the Betti setting. This is so-called restricted Betti. So if I look at there's a way to make sense of quasi-lease in the Betti, and this is just it's different. Okay, and the main theorem 2 is the Nadler-Ewan analog. There's an action of rep G check tensor I, tensor sheaves on BunG with no potency or support, to sheaves on BunG, tensor X to the I with nil cross 0. And here again, I remind you, the notion of single support changes depending on the sheaf theory. And the Betti is what we've been working with, but in general, you have to use what Sasha explained to us. So like for constructible sheaves. And yeah, so this is as formulated, it's verbatim how I formulated the main theorem in part 3. But the difference is that final ingredient up there, we don't have that literally holding in our setting. What we do have is like the right factor becomes quasi-lease. I'll call this theorem 3. Sheaves from G is X to the I. It's the same thing as sheaves on BunG with no potency or support. Tensor quasi-lease. And as a corollary, we have there exists a global Hecke action on restricted local systems. On sheaves in BunG with no potency. Yeah, I'll finish here.
Questions?
This theorem. Okay, oh, what this is fine.
Yeah, so I mean, sheaves with zero support along the zero section
Not quasi.
is the same as quasi-lease. Yeah, so I mean, it's I can rewrite this sheaves with zero single support on X. It's the same. But it takes a lot more work to prove this.
No, this is like quite. Was it this is a fine?
Well, quasi lease is like int lease.
Yeah, but this is fine.
It is, yes.
And sheaf zero, it's just a genetic condition.
If you be mentioning that,
Yeah,
And the single support is, it's conditional on single support.
but single support means different things. For like allowed to the round.
Chief zero just means.
Yeah, so it's like
no,
int
yeah,
locally
sure.
constant.
But then what is, oh, so no, I see, I understand. Because she says, what is sheaf important times? What is the sheaf important? That's it, right?
Yeah,
What does it?
I mean, the singular support of this space is in the product of nilpotent cross zero section.
That's, you're saying that's conditional single support. It's the same as just conditional important possible of this.
Yes.
Is it obvious?
I mean, having, I mean, I think it's one of like the basic properties Sasha told us, like
No, yeah.
singular support basically measures how far away you are from being locally constant.
Yeah.
And if you have single
Right,
support, zero is precisely being
Yes.
local. So it's kind of, I mean, it's a property.
Yeah. No,
Sorry, it's like, just a little confused. So I thought the sheaf zero would be the, like, not necessarily quasi least, just like. The constant things.
Oh, should I write int?
Oh, no, I guess I just,
So least means sheaf zero.
this is a small category. I just would have thought like if I take sheaves on X to the I and I put a singular support zero section, then I would get the thing you call LS of X to the I.
Yeah, okay, so this. X, Betti,
So not X is considered as a space. Side of X. So that X is straight to the space.
yeah,
Whereas on the right, it's X to the right.
so maybe put an underlying X or something like that. That good for good notation?
All the good X, if you understand that.
You gotta have different totalization.
But the point is Q lease and LS are different things, right? Q lease is strictly small.
was small. I thought it was.
So I thought that inside of LS, you have the things that are in these, the things in LS are not necessarily these things that we're discussing. And I think, right, the union fire metric, so whereas Q lease is the things that are in this.
But it was just local systems, right?
Yeah,
That's
but
all the restricted.
yeah, you should put a restricted setting there.
These are quasi like structural.
Wait, so if I put restricted here, then do I look like it? Wait, so if I put restricted, it corresponds to putting closet.
Yeah, but sorry, if I take sheaves on X to the I, and it's the Betti sense, and I restricted is something about like no, in the whole sheaf sense. And I take zero singular support, I get LS, right? So is it just that sheaves here is understood in constructible sense?
Yeah,
Ah.
yeah.
Okay,
Yeah,
so
sorry.
it's not sheaves all, it's sheaves.
Int.
It's sheaves.
Yeah, sorry,
On both sides. Okay, so-
I'm sorry, I'm really sorry. I
No,
said
no, you probably
I
said
said
it.
it earlier, and I purposefully chose to not write it down because my fingers were hurting. But yeah, sorry, sheaves in this setting means int.
As in the last few things that you said,
Yes.
right? Okay.
Yeah,
got it,
yeah,
got it,
yeah,
got it.
sorry.
Okay, got it. So we're particular for theorem 3, and this is specifically for constructed sheaves.
Yes,
You're making this
yes,
for
yeah.
theorem.
So the notion of sheaf here is not all, like it, before I had an all, it's not.
Yeah, okay, great. Now I'm
Yeah,
confused.
so-
Was that also the case for the final ingredient thing up there? Was that for all or?
That was for all.
Okay,
That was for,
so that's also true.
that's true for all. So
So
in the,
restricted in at the story. When 4 off, 6 off.
Yeah, when it-
From that area.
so in the 4-author paper at the appendix A, they explain 6 settings. There's an A, which is Betti all, A prime, which is int Betti. Setting B, B prime, B double prime, which is like the various etale settings. And then there's C, which is Rham. But I don't remember if there's an int Rham.
There's like holonomic and there's not necessarily.
Yeah, okay.
Right.
Okay, so there's at least 6 settings, but if you take sheaves here in the appropriate setting, which classically is inconstructible, then yeah.
Because I could also write the top line without the constructible restriction, and then on the right side, I would get no less. These I think it would also be the same, right?
Yeah, thank you. Yeah,
That's why I was confused.
I'm sorry, that's
No, no, no.
that's on me. I should have written down what I mean by sheets.
Any other questions? All right, let's thank this for the last time.